So today, homework 3 was due. Yeah, that's right. Okay, homework 3 was due. I sent out an email message about the lab. Someone was having trouble finding the capacitance value for that. I don't know where I found it, but I used 100 femtofarads for the pre-lab. So you're free to use that also. And I didn't try to dig through my notes. I think it's written somewhere in the lab somewhere. Pre-lab's due. We will finish lab 2 on Friday. I will be there around 1:30. I'm going to be about 45 minutes late. I've got a meeting that it's something we just have to do.
Did you say finish the lab or start the lab?
We're going to both start it and finish it. Lab 2 is a 1-week lab. Lab 3 is a 2-week lab, and you will write a formal lab report for that. And I'm not giving you a template for it. Basically, what I want you to do is just put a cover page on there. You can do whatever cover page you want to do, as long as your name's on it and EE380 is on it somewhere, so we know it's ours. It'll be uploaded to BB Learn too, so that'll be helpful. For us for knowing it is ours. There's separate sections in the lab, and the rubric is amazingly detailed because I wrote it. It says like so many points per section. So you have to look at that section and figure out what you need to put in there to document it. And I'm just going to give you like an example here. Lab 4, you have to write a report too. I want you to get started on banking for yourself more so than following the template. So like part 2. That's part of the pre-lab. And make sure you keep a copy of your pre-lab because you're going to need it for the lab. I'll give you a hint. Don't pick function 3. I'll say that again. Don't pick function 2. Function 1 is probably the easiest one to do. The required section has steps 1 through 8. Section 1 says all of these steps should be clearly documented. You don't have to put anything in your report for that. Section 2 requires you to make some calculations. So in your report, I would expect to see those calculations to get full credit for that and your results. Part 3 says create a schematic and symbol. So what I would expect to see in your report would be a picture of the schematic and a picture of the symbol. And maybe some kind of footnote saying this is a picture of my schematic for this function or something like that. You want to put enough information in it so someone who is an engineer could look at it and it wouldn't look like a bunch of gibberish, but they could actually understand what you did. As in, you know, this is my schematic for this project, or something along those lines to describe it. Part 4, you need to show that the circuit implements the function on the truth table. So I would expect to see there maybe a chart of what your truth table is, a picture of your simulation showing you simulating all those conditions and what the outputs are, and then map back up to your truth table what your values were to compare to your expected values to make sure it was right. So things like that. If you have any questions, I'll be happy to answer them, and I'll be in the lab, which will make things much simpler. And it will be just whatever Sean says this semester. I'm recording. Okay, what the heck? Management needs to hear this if they want to listen to this. Last semester, they gave me they insisted on giving me GTAs for the 380 lab. And I was not allowed to go to the 380 lab. Partially because I had class at that time. The best I could do was hire an undergrad TA who knew what he was doing, and that was Sean. And so Sean was basically covering for me in the lab. And it was a little dicey sometimes. I'm much happier having the 380 lab back. Exam 1 is going to be next week. in person, or Zach has emailed me and arranged a remote exam. So if you want to have a remote exam, you better email me this week. You don't have too many days left, just one. Otherwise, the exam's in person, pencil and paper. Body effect is one of the new things we've talked about in here. Yes, there'll be a question about, I've written the exam. I can tell you there is a question involving the body effect. It doesn't specifically say body effect on it, but it doesn't say you can neglect the body effect on it. Okay. We looked at 3 different types of ways of doing standard logic. Static CMOS, the most reliable and robust. Pass transistor, and we were looking at a hybrid pass transistor dynamic logic circuit in memories today that people actually used. So pass transistor gets used, and the basic rule for this is what's on the gate and what's on the drain gets ANDed together and comes out at the source. If I tie 2 wires together, I get the OR of that. And dynamic logic. Dynamic logic uses the same pull-down network as static CMOS. So both static CMOS and dynamic logic are inverting. Pass transistor isn't. I get rid of a few transistors on here. There's a lot of, I lose noise margins. My noise margins get lousy, but I can fit it in a much smaller space. That's where it usually gets used. Pass transistor, what's on the drain, what's on the source, ANDed together. That's AC, and this wired OR coming out. Because of the Shannon criteria, if you're given a pass transistor circuit, the function, and you just use these basic rules, the function you get out will not be in its reduced form. You may have to do a little bit of Boolean algebra reduction. It's the usual things, 3 rules nobody remembers. If you don't reduce it, I don't mark it off completely. I just take a few points off. So reviewing this, this is dynamic logic. During we don't know what the answer is here because we haven't looked at this before. During the pre-charge phase, phi is low, and if phi is low, it's low on both transistors. This transistor is on, and this transistor is off. So it is going, the answer will be the output's high no matter what. I put something that looks like this timing diagram on exams before. And then when I go into evaluate, this goes high and this goes high. Now A, B, and C matter. So A is high, B is high, C is low. So I have, in this case, I have a low resistance path through A and the phi transistor to ground. So then the node will get pulled down and evaluate. That looks an awful like many of my exam questions that I've ever written on dynamic logic. Yeah. Yes. Yeah, one of the circuits we were looking at today in memories was a tri-state buffer, which looks completely different, and it kind of throws you off the first time you see it. It's different. Okay. Anytime I have feedback in a logic circuit, whether it's just an inverter feeding back into another, or I have these cross-coupled NAND gates, you instantly think latch, because that's what that feedback is doing. It's storing the state until I change one of the inputs, R or S, to change the output. And we talked about what happens here. If both R and S are low, it's just going to maintain whatever its previous state was. If I set the flip-flop or latch, by pulling S high, the output goes high. If I reset it by pulling R high, it goes low. If I do both of these things at the same time, Q equals not Q equals either high or low. We figured it out yesterday. I have to go through the logic again to figure that out. It varies whether it's a NAND latch or a NOR latch. And you just get a logical absurdity. So don't do that. Well, this is about where we got. And I want to talk about this in a little bit more detail because I think I was fuzzing out towards the end of class. What we want to see here is how this thing works with these non-overlapping clocks. So my first state here is phi 2 is high. And if phi 2 and phi 1 is low. And these are NMOS straight thinking transistors. So if it goes high, this is on. Phi 2 is high. This one's on. This one's off. And this one's off. Okay. So the input to D is an open circuit because that transistor's off. And this transistor down here, the phi 2 transistor's on. So I've got this loop through here. And all this feedback loop is doing is it's maintaining the previous value of D. Now, whatever value is being maintained is being passed through to this transistor, through that transistor, through a double inverter that goes out to Q bar and not Q. So it's maintaining the previous state as long as phi 2 is on. So we'll call this maintain. Now the next thing that happens is all the switches turn off to keep bad things from happening. The bad things would be that it just doesn't work anymore. The next step is this one right here. Phi 1 goes on and phi 2 is off. So phi 1 is on, this transistor goes on, this transistor turns off, this one goes off, and this one turns on. So if this first transistor here is on, it's going to take the value of D, and the feedback loop is disabled because that transistor's off. So it takes the input of D and passes it through this double inverter, and this will be the new D. This transistor is still off, so the new D is going to get stored right there. I haven't changed states yet. This is when I'm loading the new D in. And now I need yet a third color to get the flip and the flop. Thank goodness there's people here. I said, thank goodness there's people here. I don't feel like I'm talking to my computer screen and laughing at my own jokes or attempts at jokes. Okay. So we put a little bit of time in there, this non-overlap interval, to make sure all the transistors turn off. And then I go back into the orange state, basically. This one goes off. This one goes on. This one goes on. And this one goes off. And we're flipping and flopping between these two different states. You know how I got the name. Okay. Since this transistor is off and this one's on, the new D is being cycled through this loop, this orange loop. And it's being maintained. And the new D is also being fed through here. So now the new D makes it into the second stage. and this transistor's off. It gets buffered and passed to the output. So it takes a full cycle in here of this going high and phi 2, both phi 1 going high, a little break, and then phi 2 going high in order for the output to change. Now phi 1 and phi 2 are generated internally off the clock. So basically what you want to do is you want to make this load new D happen on like the leading edge of the clock, of your master clock. And you want to internally generate a clock, a short pulse off of your leading edge of the clock, and you can control the timing of how long that pulse lasts and how long this pulse lasts. This first pulse here is going to control something called the setup time and T setup. While T setup, while phi 1 is true, which is going to equal, for however long that is, which is going to equal our setup time, I have to maintain D stable. Because if D is not stable and it changes during that time, I'm going to get a different value loaded in. So during this whole time, D has to stay stable. I've got this other thing down here, and this is like the whole time. I have to hold it stable after the clock edge. So I cannot have my D changing right before the clock edge or right after the clock edge, or I will get errors. Okay. The person who generates these clocks does it with delay lines inside the flip-flop. And usually the way you make delays is you put like really small inverters in there, really small buffers in there that are really slow. And you generate a stable delay off the clock edge to generate phi 1 and phi 2.
Why don't we just take some RC?
Because ours are really hard to build inside integrated circuits. And inverters, slow inverters are really easy to build. I make the L big. I make the W small, and I can get it really small.
Diagnostic testing improved identifying variants. For positive news on the vaccine front today, in more than 27 million Americans have received one dose of the vaccine. More than 6 million have had their second. Johnson & Johnson.
Somebody's paying attention. This is, okay. This is the thing, the one thing I want to translate from the Zoom world to the real world. To imagine if you could just walk around.
I agree.
Small children, little yappy dogs. Yeah.
Yeah.
Okay. So this is the difference between a latch and a flip-flop. We have to put extra circuitry in the flip-flop to make it edge triggered. And it's an art form, and it's something that Bruce Hancock should do. It's only, the output can only change right at the edge of the clock. And you usually design the flip-flop to either be rising edge or falling edge. Most right-thinking people do them rising edge. I've got to keep D stable for at least this long, we'll call that the setup time, before the clock edge, in order to guarantee that the right data gets fed in. And I need to keep D stable for like yay long after the clock edge in order to ensure that it actually works right. So this is called the setup time, and this is called the hold time. Now, a latch is much easier to build. Someone like me could do that. It's level sensitive. In Brower's example, she's not using a separate enable for it. She's using that clock signal as an enable. But basically, when the clock is high, because it's acting like an enable, the latch is transparent and the input gets fed immediately to the output. When the clock is low, it's latched and it's going to go back into that feedback loop and maintain whatever value it has. You're going to get amazingly different results whether you pick a flip-flop or a latch. Flip-flap, well, that's the one my mother called a remote control, and you cannot break her from that habit. It was a flip-flapper.
I thought you mispronounced the first.
Well, I did. I mispronounced flip-flop. Okay, but yeah, and it's just, when I hear that, I hear myself say that. No, I don't want to turn into my mother. Now we want to look at this diagram and see how different this is. We've got an S, we got a D. Oh, thank goodness. We've got a D. We have a D flip-flop or D latch, and we want to see what Q does. Well, as long as the clock is high, it's transparent. So it's going to be transparent in these times. And I'll try to draw it more neatly. So D's in whatever state it is. We don't know what state it started out in. So I'm going to put a big X here. As soon as the clock or the enable goes high, D's high, it's going to stay, and it's going to go low here, and it's going to stay low. It's because it's going to hold the value when it's low. When it goes high, it just immediately tracks D, whatever D's doing, immediately. And then it goes low, it ignores that pulse. It picks up this pulse because it was high, and it goes back down, and it will pick up this pulse. So this would be the output we would expect from a latch. Now, if I had a flip-flop in here, again, we don't know what the value is before that first clock edge. It's whatever value it had stored on there. But when I get to the clock edge, D's high, so it's going to stay that way until the next clock edge, no matter what's going on D. At the next clock edge, it's high, so it stays there. At the next clock edge, D was low, so it's going to drop low. And at the next rising clock edge, it's low, so it's going to remain low. Drastically different outputs from the two different devices. So you write your Verilog code for a latch, you may get completely different results than you do for a flip-flop. Okay. What is this thing? I can't do timing delays with this stupid pencil. There are delays through all these circuits. And when you kind of looked at that, well, this is what we're going to look at in lab 2, is timing delays. And with our timing delays, what we're going to find is it takes a finite amount of time, even through an inverter, for once the input changes before the output changes. And you can imagine with a more complex circuit, where like a flip-flop where I have, or a latch, where I have multiple NAND gates and NOR gates and delay lines and things like that, the delays are going to get bigger. She says this, but this is never true. There's always a delay. We have to figure out what the acceptable range of operation is. Obviously, if we have a clock that's running like this, this is our clock. If our delay time is greater, getting the data through the flip-flop is greater than a clock cycle, we obviously have a problem. That's not going to work. Typically, we designed everything to have a maximum delay, and the delay is going to depend upon how much capacitance the output has to drive. And the capacitance is dominated by the number of gates, the gate oxide capacitance. So if I put 10 inverters off of this output, the delay may be like here. And this is called a fan out of 10. And I will talk about fan out in lab 2. It's going to have a much higher delay than if I only put one gate on the output. Fan out of 1. The way we designed our circuits was we designed them so that with a fan out of 10, the maximum delay would be a half a clock cycle. And that gave us a factor of 2 for safety before that next clock edge. That's what I wanted to say about this today. Okay, this is really bad. And I've seen stuff like this, like when people testing stuff like this at Micron when we were there. Let's set this up to make it purposely bad. What's going on here is you've got this clock edge, and exactly precisely at the clock edge, and this is one thing that Becky was talking about in 310, was that you decide to change your D input at the same moment as the clock edge happens. What does this device think D is? Sometimes it thinks D is high. Sometimes it thinks D is low. And this is called metastability. You've purposely set this up so that Q doesn't know what the answer is. There are other things you can see in here and this is called jitter. And you'll hear me use this expression frequently from now on. I don't know if you take more classes. You can see that sometimes I get this clock edge here, or sometimes the output switches here. Sometimes it takes a little bit longer to switch. And sometimes when it's really having trouble making up its mind, it takes a really long time to switch. And this is called the clock jitter. And you've got to keep the jitter on these devices down to a small fraction of whatever your clock cycle is. And it's things like jitter and setup and hold time that determine how fast you can run your clock. So when you're trying to push a process and maybe the process was designed for 10 megahertz clock and suddenly your boss wants you to take pictures twice as fast, so you're going to use a 20 megahertz clock, you have to like stop and consider this. Sometimes it works and sometimes it doesn't, depending upon how much of a margin of safety you've added into that design. And yeah, my boss.
So in this case, the stability, the top flap represents going high or low when you switch the same time to low high.
Right. So it's probably what you have on here. It doesn't say what the channels are, but you probably have one of those signals is either D or the clock, and the other one's probably Q. Yeah. Wait till we get to I diagrams. Oh, that's 490. So in order to do this, what you have to do is you've got to set up a target for what you want your setup and hold time to be. Bruce told us, and we all believed him, that you want your setup and hold times to equal each other. And they have to be a small fraction of the clock. I don't know why, but he said so. So we just, yeah, we all agreed. So you got to meet those setup and hold times. You've got to make sure that your inputs are not changing right before the clock and they're not changing right after that clock. That's not as hard to do as you would think, because usually what causes signals to change is the previous clock cycle. So as long as your circuits are fast enough to settle in that first half of the clock cycle, you've got a half a clock cycle of headroom. And that's basically what we ended up doing. I wish I could find Bruce.
I would guess. You're a great guess.
Actually, no, we wouldn't even.
I
Okay. The one who would be really fun to come talk to you guys would be Ken McCarty, but you probably yell at him about menographics. He's the one who originally trained me to use menographics, and it was such a thankless job that menographics went out and hired him because they figured, I guess if you can train me, you can train anybody to use this stuff. I can be a computer idiot when I want to be. But it was really nice because then at that point, part of his job was to support customers and support customers at JPL. So I had this phone on my desk, and we actually had phones on our desk at the time. And I just call, whenever something wouldn't work, I just call him directly. I had both his cell phone numbers too.
There's no escape.
There was no escape for me. He's retired now, gratefully retired. He's still talking to me.
There you go. That's a perfect chance for anyone to get.
Yes. So what we want to do is we want to set this thing up. So we've got D, and let's see if this one passed. Okay, we're going to say D is changing. Did it catch the change to 0? We have to look at the output. The output went to 0, so it caught it. So that has to be, that time right there would probably be greater than T setup, because it caught the change. If the change happened long enough afterwards, in this case, this change happened long enough afterwards that it didn't affect the input, then this time would be greater than T hold. And keep in mind, you don't want to run things right at, oh, I'm going to change it right at T setup time, or I'm going to change it right at T hold time, because of jitter. Timing variations on the clock edge happen all the time. Timing variations on the delay happen all the time due to temperature changes, the phase of the moon, or whatever the heck controls that. But it's never exactly the same twice. And that's why you saw like that range of values in that diagram. Wow. This is the most time I've ever had to spend on this. I've done it in 2 minutes. I've done it like in 5 minutes before. Look, set up and hold time. Set up. Good, bad, doesn't work. Okay. We want to see if we want to, right here, we want to see if it and this is the way we would actually simulate the way Bruce would simulate these, is what he would do is he'd set up a simulation and he would change when D changed. So it's like a time sweep on his simulation. He might do one here, and he might do one here, and he'd vary it like a million points in between to find out exactly where that sweet spot is and where it was enough time beforehand, and call that T setup. We have to simulate this too. So I've got, and it was an analog simulation of a digital circuit. The only way you can do a time sweep is with an analog simulation. So right here, I have D changing this amount of time before the clock. It didn't catch it. So this is a T setup violation. It didn't work. It changed too soon. Now right here, I have the same situation. D's changing right before the clock edge, but it caught the final value. So this is T setup pass. And you could vary that time and find out exactly what your setup and hold time was. I don't think anybody in here will ever design their own flip-flop.
I mean, you never know.
You never know. You may go to work for Xilinx. It happened to Brad Turcott. That was his first job out of college, working for an FPGA company that all they do is design big arrays of flip-flops.
I have a question.
Yes, thank you.
So on B, we have the time setup as a pass. What is that on the left? VIOL.
It's a violation. It's short for violation.
And is that because Q did not really respond to what happened?
Yeah, D changed before the clock edge, but Q didn't. It wasn't enough time before the clock edge for Q to
So it needs
notice.
time to take in what's happening in order
Right.
for Q to respond, and that's our setup time, right?
Right, because
Okay.
it's going to take time for the signal to pass through that first Phi 1 transistor, and it's going to take time to go through that buffer. So they've got all those delays in there. So here I've got D changing a little. Oh, these are all setup time. I was wondering what was going on here. I've got D changing a little bit before the clock. It's going low, and my output goes low. So my T setup has passed. And here I've got D changing a little bit before the clock, but it's not enough time for it actually to pass the Q. So I've got a T setup is failed. It's a violation. The other word. Okay. So that's setup. And when we're looking at setup times, we're thinking of things changing right before the clock edge. Now with hold time, our concern is how fast does it change after the clock edge? So this would be the hold time right here. It's after the clock edge. And D changed after the clock edge, and Q caught that. And we didn't want that to happen. So this is T hold failed. And if I go here, I've held it for this long after the clock edge, and my output remained low, so T hold passed. Right here, there's my time, my clock edge. It caught the change and not the original value, so T hold failed. And here I have, there's my hold time, and it kept the held value, the value that was before the clock and a little bit after, so T hold passed. You might do this if you're working at like Micron or something like that. They do some of their own little custom weird digital circuits. Okay, what are these things is not like the other. Okay. Tell people was raised on Sesame Street. So we're looking for setup. So this is the clock, the D changes right before the clock, and it picked up the change value. So we've been able to, we had an adequate amount of time to be, this, I don't know how to say this. We had enough time here. This was within the T hold time, T setup time window. So we didn't catch this edge, we caught this edge. So this edge change was too close to the clock edge. This one here, again, it kept it. No, okay, so it kept the right value. This one was far enough away from the clock edge that it kept the old value. Okay. Okay. I don't want to do any more of these. It's the same thing. Oh, okay. Oh, wow. we'll talk about the example a little bit. I knew this was going to happen. Don't ever do this. This was my solution to this problem, is just don't do this. I had to do it once. This guy from Johns Hopkins showed up. He was an astronomer. And we had our cameras, we were little cheap cameras, were faster than anything anybody else had. And he wanted to look at these high energy events that happen very rarely. So a high energy particle hits my imager array, and he wants to take a bunch of pictures of it really fast. He doesn't care about the whole imager, but he wants the area of the imager so he has a chance of maybe catching one of these a year. So it hits the array within 200 nanoseconds, which for us was 2 clock cycles. I had to read out the address of where the particle hit by looking at a threshold detector, subtract 5 from it, and then read out a 5x5 window around this device, repetitively really fast. Because we could read out, and so he could take pictures of this high energy event happening.
That whole process took place in just 2 cycles.
2 clock cycles. And there's an adder involved. And you know how slow adders are. And it's a 10-bit adder on top of it. Yeah, because adders are inherently ripple. The previous state depends upon the past state. The only way I could do it was to turn the 2 clock cycles into 4 clock cycles, which was basically I was using both a positive edge triggered flip-flop and a negative edge triggered flip-flop in the same system. Clocks are notorious for being, if it's like 100 nanosecond clock cycle, that doesn't mean it's high for 50 nanoseconds and it's low for 50 nanoseconds. It's high for 40 nanoseconds and it's low for 60 nanoseconds. So the timing it's not just a factor of 2 you have to worry about, it's more like a factor of 4 to get everything lined up and everything. And yeah, I spent like weeks on that circuit. I got it to work. Yeah, but okay, so just don't do this. You don't want to mix your clocks, especially like, look at this right here. I've got a 20 megahertz clock and I got a 50 megahertz clock. Those are not multiples of each other, and they're not synchronized off of each other. So it may happen sometimes these clock edges coincide. Sometimes these clock edges are really close to each other, and sometimes these clock edges are far apart. And if these clock edges happen at the same time, and this is changing right as this is changing, you may have a metastability problem with flip-flop number 2, because they're both loading in at the same time. It's not a good idea. This is better, but it's not great. This is called a synchronizer. And basically what I'm doing here is I'm running this through 2 delays just to kind of like this one may be, these 2 may happen at the same time, but it's going to take a whole clock cycle before the output goes into the rest of your circuit and messes it up. So it's more likely to work. This is why, okay, you know about DDR memory, not flash, DRAM. Most DRAM memory is like a DDR4, I think is what they're selling now. I've seen DDR6 stuff too, but that's like experimental. DDR means double data rate. And the way they get there is they actually, to get to the double data rate, is they actually clock things in on both the leading and the falling edge of the clock. And it's because of the 40-60, the clock edges aren't always stable. and they jitter around and bounce with time. They don't actually do it off of the falling clock edge. They latch the first bit of data on the rising clock edge, and they put an analog circuit in there called the delay lock loop that will latch the second signal in at half the expected clock cycle. And then they go to DDR2, so now they're getting 4 data byte bits out every clock cycle. So they have to like have if you're using the delay lock loop, it helps, is that instead of, if it was 100 nanosecond clock period, they have 1 clock that goes off at 0 at clock edge, 1 clock that goes off 25 nanoseconds later, 50, and 75, and then rely on the system clock to do that. It is so bad by the time you get to DDR6 that the output's running, the data's coming out so fast. They are deciding what the data is before the output has had time to settle. And what they do is they look back at the 4 previous values of what the data is. And if they're all high and it's coming down a little bit, you can say, oh, it must be a 0. And if it was like, if they were all zeros, then, and it's coming up a little bit, you can say, oh, it must be a 1. And if it was like a 1 0 1 0 1 0, it might be somewhere in the middle, but it's coming up a little bit or coming down a little bit, and they have like a whole analog circuit to predict what that means. Okay. Summarizing everything. What have we done so far? And this is kind of like, we'll kind of like do a little pre-review of the exam. We've gone through and we have reviewed what you learned about MOSFETs in EE380. So the basic things are transistors. Can you look at a transistor picture and tell whether it's NMOS or PMOS? Can you tell which is the drain, the gate, the source, and the body, looking at the picture and maybe the associated voltages? Can you calculate the current? Once you know the drain, the voltages, can you tell me what region of operation it's in? Then can you calculate the current based upon the region of operation? NMOS and PMOS region of operation. If you know the body voltage, do you know how the body voltage is going to affect the current? Because it affects the threshold voltage. So you have to recalculate the threshold voltage to get the current. If it's in saturation, you have the additional thing of the output resistance affecting the current. Okay. Do you know what a cross section of a MOSFET looks like? Are you able to label all the parts of it? Do you know what the top view of a MOSFET looks like and how to label all the parts of it? And then we reviewed static logic circuits. Expect one of those on there. We also looked at pass transistor and dynamic logic. I typically put at least one of those on there, sometimes 2. One of each. And then what else have we done? Body effect. Capacitors. Oh God, no. I'm not going to make you calculate capacitors on the exam. And we've looked at latches and flip-flops. So that's kind of what we've done. And I actually I did have forethought in this. I was thinking, oh God, why did I do that? I went ahead and loaded these in because I thought we may have a little bit of extra time. It's done. It's really not that bad. Did you take 380 last semester?
No, I was about to, but then I got kicked out.
Okay, all right. 380 last semester was horrible. I'd just be glad. What I did was I reduced it from 2 exams to 1 midterm exam. And it was too much information for 1 exam. This will be the easiest, exam 1 will be the easiest exam you will see in here all semester long. So be prepared for this one because it may be the one that keeps your grade up when it starts to slide later on. If you can, generally it comes out, I at the end of the semester, I draw a line somewhere in the grade book and I say, okay, if your overall average is above X percent and your exam average is above X percent, you're exempt from the final. And you don't want to take the final because the final is like the worst test you'll ever see in your life. It's just a lot of information, okay? So try to keep up with the labs and keep up with everything, and then you get an early graduation present or whatever it is. You can bring in a sheet of paper, formulas, diagrams written on it, front and back. Save it for exam 2 in the final. It's going to be cumulative. Exam 2 is going to be mostly analog, whereas this one is mostly digital and MOSFET basics. And the final exam also includes things like, oh no, frequency response, Bodie plots, you remember those? And ADCs and DACs, might as well just throw that in there too. Yeah, ADCs and DACs. It's almost like stuff you learned in, no, what's that class? 286. How it's the architecture of the ADCs and DACs more so than using them. You can use a calculator. A ruler may be helpful. If you can draw, there will be places where you have to draw diagrams. And if you draw sloppy diagrams and I can't read them, I don't give you credit for it. Make sure you label your diagrams. Things like this axis is voltage, this axis is current, you know, whatever you want to do. Put the labels on there. It helps me realize that you know what you're doing. There's 7 problems total, worth a total of 104 points with 1 point extra credit. So your maximum score is 105 out of 100. That said, there have been people who made like 110 on it. There's stealth extra credit. If you fill in all the blanks, every blank, things like Quest, it's worth a point. There's sometimes people draw cartoons on their exam that make me laugh, and that's worth a point. Sometimes people totally bomb a problem. They don't know what they're doing. And they write on the side of the paper, I have no idea what I'm doing here. And the fact that you realize that is worth at least a point.
What does this circuit do? It lets the smoke out.
It lets the smoke out, yeah. So just, grading exams is boring, entertain me. This is the information you get on the first page of the exam. You can use it anywhere on the exam. So you've got a threshold voltage here. It's VT0 without the body effect, VT0P without the body effect. You've got KN prime and KP prime, and that should be micro, not mega. It shows up correctly on the exam. That's the font of these slides. I've got lambda, which means I'm going to use the lambda in the RO equations and in the saturation equation, not VA. I've got this gamma, which is the body effect parameter. I'm given VDD. I'm giving the magnitude of phi f. This is kind of a dirty trick because in the formulas, the formula always has a magnitude of 2 phi f. So you got to remember to multiply that by 2. The minimum length of the transistors, and I'm given the basic parameters for capacitance. If I made you do something awful like calculate capacitance on there, you get the charge on an electron, epsilon naught, and the relative permittivity of silicon and silicon dioxide. All those can be used freely anywhere you want to use them on the exam. And yeah, you guys know about this by now. If you see any questions like this, just answer them. They're worth a point. You make me laugh. Sometimes I give you 2 points. What we've covered so far: CMOS inverter noise margins and area. We looked at the MOSFET structure, current voltage characteristics, delay and power. I'm not going to expect you to know those equations off the pre-lab, you know, like the alpha and the big long equation for calculating TPHL and TPLH. But you may have to look at a diagram and tell me if I give you a yeah, that's really clear, isn't it?
I mean, I know what you're trying to say.
If I give you a voltage versus time plot of the input and the output of an inverter, you might maybe look at that and estimate what some of those delays are. And you just like quiz 1 in the lab, you being able to estimate what VO high and VO low and the noise margins are. Being able to do those standard CMOS circuits, yes, I care about that more than anything. People have told me, several people have told me who've had Micron interviews, Micron screening interview and my exam 1 and 380 are about the same thing. So if you have an interview with Micron, this exam is a really good thing to go back and study. You know, at the career fair or something like that. And it'll get you in the door for a second interview. We talked about the body effect, capacitance. I've never put a capacitance problem on an exam. Past transistor logic circuits often show up on the exam, and dynamic logic circuits often show up on the exam. There's always a problem with the body effect, whether I say it is on there or not. I may not even use the word body effect. The big tip off is you know what the body voltage is, and it doesn't equal the source voltage. And then latches and flip-flops. And that's pretty much what we covered. The other things from the lab, be able to do the things that you see on the lab 1 and the lab 2 quiz. You haven't gotten the lab 2 quiz yet. The lab 1 quiz, and I already said all that. The estimating, if I give you graphs, can you estimate the delays, and can you estimate the noise margins and the VOLs and all that stuff, and know these symbols. If the arrow is on the body, okay, so this is an NMOS, but if I put the arrow on the body of, and it's an Audi, if I put the arrow on the body of an NMOS, it would go like that. And the same thing here. This one would go this way. The one with the arrow is the source, if you're lucky enough to get that symbol. If you don't have that symbol, if it's NMOS, the lower voltage, for NMOS, VDS is always positive. That's how you define drain and source. And PMOS, VDS is always going to be negative. So whichever one is the higher voltage is the source. Okay, and I'm done. Any questions about the exam, life, the university, anything?
Actually, yeah.
Yeah, okay, Sean.
For next week,
Yeah.
do you know what we find the link?
Yeah, I sent you an email
Oh,
and it said 100 femtofarads because that was the number that I used in my solution. And I don't know where I got it from. It was either in the lab or it was in the data file at one time and I accidentally deleted it. I used 100 femtofarads, so that's
Hey, Julie.
be grading. Yes.
So just to make sure, which day is the exam on?
Oh, the exam, if you're taking it in person, the exam is on Thursday, February 11th. And if you're taking it remotely, I'm trying to schedule everybody on Wednesday, February 10th. I cannot, I'm somewhat limited in my multitasking abilities. There's somebody in 280 who insists he wants to take it during class. I'm like, no, I cannot watch an exam in the classroom and an exam on Zoom at the same time. Because I'm going to walk away from the screen and you're going to be sitting there yelling at me, and I don't know what's going on. So yeah, I'm trying to schedule it, like the day before. But just send me an email and I'll give you times, and we'll make sure it fits into your schedule. Okay. So for in person, it is Thursday, February 11th at 4 p.m. Okay.
How long is the online exam going to be? Like, is it going to be presented on the internet and we simply write it down and then we submit it by taking a picture?
When we do it online, basically what you do is when you come into Zoom, I will email you the exam. Well, when you come into Zoom and you turn on your camera and you turn on your microphone, then I email you the exam. And from the time I email you the exam, you have 75 minutes to get it back to me. Same as the length of the class. And it's going to be a similar exam, but not identical. And when you get it back to me, I take it and I print it out and I put it in the pile with the other exams.
All right, thank you.
Okay. But if you want to do that, email me beforehand, because I get really confused easily.
Yeah, I just sent it like a couple minutes ago. So just to reiterate, it's at
Okay.
Wednesday, 4 p.m.
No, it won't be Wednesday at 4 p.m. because I'll be in class then. It'll probably be like noon, starting noon to 12:45, if you can do that.
All right.
Okay.
Sounds good.
Okay. Yeah. Okay. We're done. Okay, I'm going to stop recording at least.